Yeah, well, it gives you guys an advantage if it's not really legible.
Have you looked at the exam yet?
I don't know the exam exists yet. But no, I haven't. I normally see it just a little bit before it's done, and then I provide comments to Professor Burke. And normally my comments are, here are ways we can make it a little bit easier. So like, the quiz, we took out an extra layer of insulation on problem 5, just so there'd be like one less set of conductivities and radii. Okay. But no, I haven't seen it yet. Okay, so the quiz hit pretty hard. I hope nobody's feeling too defeated.
My first D in my life.
What'd you say?
The first D I've got in my life.
It's not really a D though, because if you got, the mean was a 65. So if you got a 65, it curves to like a B+. So if you did better, mazel tov. If you didn't, it's fine, there's only 5 points. There's tons of points left to get in this class. In fact, so far, you have the most points anybody has in this class is an 8. Right now, everybody has a desperately failing grade because the other 92 points have not been awarded yet, right? All the final, the midterm, the other quizzes, most of the homeworks. So right now, everyone in this class has between about a 5 and an 8. So nobody's even close to passing. Yes.
How many quizzes are we having?
4, I think. 4 quizzes, which are 5 points each, plus a midterm, which I assume is another 20. 10 for the homework, that brings us to 50, and then is it 50 the final? That sounds like, it's something like that. The final is going to be pretty heavy, I think. Okay, so the midterm's 30. Midterm's 30? Okay, so then 40, 30. Okay, and then kind of that washes out everything that's happened so far. Okay, so my observations, I graded all the quizzes. Most of you guys did pretty well on 1, 2, and 3. There were some mistakes on 3. Those were a bit more common. Do you guys want to take time to review the diffusion equation? I don't feel strongly motivated to either. Okay. 1 and 2, let's just quickly talk. Because those are kind of inverse problems. I think most of that was like the first week or 2 of classes, and then we haven't come back to it yet. But solids, liquids, and gases, which ones are the best, kind of net of everything else? What's going to be better at heat transfer? What's a better conductor? Solids. Why are solids better conductors than liquids or gases? That's for metals in particular. But in general, solids are more structured, they're denser, so it's easier for vibrations. Liquids are really bad conductors. Why? Yeah, they're not dense. So it's very hard for particles, high energy particles, to transfer that energy. Vacuums are better or worse? Worse. Vacuums are a great way to make not good conductors, but good resistors, right? Good insulation. So if something's a good conductor, it's a crappy insulator. It's got low resistance. If something's a good resistor, good insulator, it's got bad conductivity. So for those problems, I think the one that was a really good conductor is aluminum, and the one that's a really good resistor is carbon dioxide. Okay, so that's problems 1 and 2. We won't talk too much about problem 3. Problem 4 was the cylinder with internal heat generation. The grading on that was very simple, and I'm sorry if, for those of you who showed some work and didn't get partial credit where you feel like you might have deserved it. We just kind of needed to pick a simple stick and go with it. What we did was 30-point problem. There were 3 graphs. You got 10 points for each graph. I'm going to take a little bit of time to review that today because I don't think I think we did it a little bit yesterday. Do you guys feel comfortable with what Professor Burke did in class yesterday? Yes.
Can you go over the equation for the cylinder in appendix C that has like the 2 terms, the negative r squared and ln of r? Because Burke said it cancels, but I don't know how it cancels because of symmetry or something.
Oh, the ln r cancels with boundary conditions, I think.
Which boundary conditions?
Can you read me the equation? Do you have one?
Yeah, let me get mine.
It's because it's ln r. So I think it looks something like this: that your temperature for a cylinder. By the way, this is for a cylinder with internal gen. So T of r is something like C1 r squared plus C2 ln R plus C3, something like that, right? Is that correct?
I mean, it's a lot of terms, but yeah.
Okay.
A lot more terms.
So why does the ln R cancel out? So let's just draw each of these expressions. What does R squared look like? Because we're basically just superpositioning three different curves. R squared, okay, you guys aren't answering because you know it's quadratic. What does C3 mean? You're just adding C3? Yes, just a constant. So basically, if you add these two together, I wish I had more colors of chalk. Basically, you're offsetting your quadratic by something. Now, what if you added a ln R there? What does ln R look like?
What is that?
Okay. What's ln R look like, Nadia?
What is what?
Ln R.
Ln of R.
Ln of R.
Ln of
You guys don't say ln?
No.
No.
Lon.
Yes,
I have an uncle named Lon. I don't know that it's short for anything.
Isn't that like flip?
Yeah, it's like flip. So ln R looks like this. It goes to negative infinity at R equals 0. Which doesn't work for any reasonable thing on planet Earth when you're talking about temperature. So the reason that we know this C2, that this whole term has to disappear, is because we know that the temperature at 0 is not going to be negative infinity, right? That ln R, if it was allowed into this equation, would trump both the first and the third term, right? Because any number plus minus infinity is minus infinity.
Are
Okay.
the speakers on?
You want me to?
Yeah.
Does that ln term ever dominate an equation, like realistically, or is it always canceled out by boundary conditions?
It's a ln term. I mean, there are occasionally a ln term will stay. So like in your normal cylindrical shell, you've got like a ratio ln.
Yeah.
The reason in a cylindrical shell it isn't a problem is when you're dealing with a cylindrical shell, the whole thing is bounded between Ri and R out, right?
Okay. So it's
So
because
you'll have a ln term, but then this is all kind of make believe.
so there's no way you can have a full object with a ln term.
A solid object with a ln term, no, I don't think so. Nor can you have a solid object with a 1 over R term, right? For the opposite reason. Because a 1 over R term tells you it goes to positive infinity at R equals 0. Is that legible? Yeah. So we know that temperature is never going to go to infinity. I say, if we gave you kind of some abstract problem where that term did last, that would be a really great discussion point of obviously this thing can't persist at, as R goes all the way to 0. So like for your cylindrical shell or a spherical shell, you kind of get incongruity when you go to a very small inner radius. And that's kind of that's where the math might start to diverge from reality a little bit. Okay, any more questions on that specifically? Okay, I want to really quickly go through how I solve all of these sketching problems, because for those of you who've been here for the last couple of weeks, we've been working on this strategy for solving all derivation problems, where we go through an energy balance, or we state a control volume, we go through an energy balance, we do a Fourier's law substitution, and we kind of work through. But the first step, or the 0th step that we developed last week, is this commune with the problem. Let's actually kind of draw out what we think the solution is going to look like. So as we move forward, we know what to expect. Basically, those sketching problems where you do heat rate, heat flux, and temperature distribution should only take a few minutes. If you kind of just meditate with the problem for a minute and just look at the different expressions, you can normally sketch those out pretty quickly. So those, hopefully if we get this down, that will be like a gift if something like that comes up on the midterm, because you'll be able to get full points on it without much of a time commitment. So let's, do you guys want me to do the cylindrical problem again from the midterm or from the quiz, or do you want to, I'll do a sphere with internal heat chain. Okay. Okay, so a sphere with internal heat chain. I have a liberal arts degree, so. Okay, so typically when we talk about internal heat gen, it's not always the case, but we normally assume uniform volumetric heat generation, which means you've got some term Q dot, and it is in units of watts per meters cubed. Now with these solid problems, typically, this was another bit of confusion. Your control volume for when you're dealing with a solid, you normally